All right, guys, today we start a new chapter over work and energy, and we're primarily going to focus on energy. I've drawn a little diagram over here off to your right. If you want to, go ahead and you can pause the video and copy this down. Usually the way I'll start out is I'll say, think about what you already know about energy and see how many different types of energy you can come up with. The students can usually come up with about 3 or 4, but to save time, I've gone ahead and written them all out and put them inside of these circles. These circles represent something. So what we're dealing with in physics, in Newtonian physics, is mechanical energy. We're doing Newtonian, what's called Newtonian mechanics. And we're dealing with moving objects, but there's really lots and lots of different kinds of energy. So what I have in my bubbles here are thermal, chemical, nuclear, electromagnetic, electrical, light, and sound. I've put these in orange and I put these in blue. These are primarily physics focused. So if you're doing light, sound, electrical, you're dealing with physics. If you're doing the other 4 over here in orange, you could be doing chemistry or physics. And one of the areas of study is called physical chemistry, and it's a synthesis of physics and chemistry. And we see these 4 in PChem, what's called PChem. This would usually be in blue because we think about this as being a physics type emphasis, but I put it in red because that's what we're focusing on. Now, when I look out at my classroom, I right away can tell who has high energy and who has low energy. And the way that I can do that is if I see someone and their leg is bouncing up and down and they're wiggling a lot, I think that person has a lot of energy today. If I see somebody and they're slumped down in their seat and their eyelids are a little bit heavy, I think that person has low energy. But if I just took a picture, like a still frame, and I was looking at that, and I wanted to know if someone had high energy or low energy, it might be difficult to tell because I can't see those things. I maybe can't see a leg bumping up and down, or I can't see someone getting progressively lower in their chair. So to determine if energy is present or not present, a lot of times we have to have the ability to compare it to something else or to see a person in context. And that's also true for all of these kinds of energy. I can't necessarily just go and dip my finger into this mechanical energy bubble and tell if I've got mechanical energy present there. I have to either compare it to something else or I have to see it acted out. So let's start off with how we define energy, first of all. So the first thing we're going to talk about is the definition. And we're going to define energy. So energy, and the abbreviation is always a capital E, as the ability to do work or the act of doing work. So what we're looking at here is if we talk about the ability to do work, we're talking about potential energy. You have the potential. If we're talking about the act of doing work, this is the work actually being performed, or we have movement, and we're going to call this kinetic. So our energy is going to fall into 2 different spheres, either potential or kinetic. I'm going to do an autofocus here. I feel like I'm a little blurry. I don't know if this will help or not. Not so much. So if we're talking about potential energy, if we're talking about the ability, what we have to have here is we have to have a reference. I should parentheses this so far. So if I'm talking about gravitational potential energy, and we will later, I'm talking about the ability to do work in reference to the ground. If I'm talking about a spring potential energy, I'll have to talk about the potential of the spring to accomplish work based on its compression. So if I'm talking about the act of doing work, this is always going to relate to movement. Now, again, we're going to be talking about mechanical potential energy and kinetic potential energy, but each one of these bubbles, and the reason, well, I'll explain the overlap in a minute. If we're talking about thermal energy, we're looking at the movement. If we're looking at kinetic thermal energy, we're looking at the movement of molecules. If I'm looking at kinetic electrical energy, I'm looking at the movement of electrons through a metal. If I'm looking at the kinetic energy of sound, I'm looking at waves moving through a medium. So this is always related to movement. And that's what we see for work. So work is always tied to movement. So we have a connection here between work and movement. And we're going to see later that the definition for work is a force that operates over a distance. And here we're moving this distance. So here is that tie-in with movement. Because we really don't have the ability, as just to reiterate, we don't have the ability to just look at something and say, oh, this has got X amount of energy. It has to be a comparison. It has to have a reference point, and we have to actually be able to see it happening. That takes us to point number 2, and that is that energy is what we call scalar. So number 1 was our definition. Number 2, energy is scalar. This has a value. There is no direction to it. This also means that we look at the start point and the end point only. We don't care about the path in the middle. The pathway is inconsequential. Inconsequential. So in other words, we're talking about gravitational potential energy. I'm going to give energy to something by picking it up and setting it on a shelf. Maybe it's a really heavy box and I pick it up and I get halfway up and I have to pause to kind of tighten my stomach muscles. So I lift it and I wait, and I lift it a little more and I wait, and then I set it on the shelf. Energy doesn't care. It only cares about my starting point and my ending point. How I get there in the middle doesn't matter. And so again, we're looking at having those reference points as being really important. The third thing about energy, so we're going to number 3, these colors again. Let's go to green. It is conserved. Energy is conserved. So I have mechanical energy, and the mechanical energy doesn't always stay in this bubble. You know what? Let's go over here. So I have nuclear energy, and this nuclear energy creates fusion in the sun, creates electromagnetic radiation that gets sent out towards the earth, and then that gets picked up by plants, and it gets turned into chemical energy in the form of ATP. First glucose, and then organisms take the glucose, they turn it into more chemical energy in the form of ATP. And we burn that ATP in our mitochondria. We burn the glucose in our mitochondria to make ATP, which is a byproduct, creates thermal energy. So we see energy that can flow. But law of conservation of matter and energy says matter and energy cannot be created or destroyed. It can only change forms. And we see it change forms all the time. But I'm not going to write all of that out. Hopefully you know that, and hopefully it's review. So what we're going to see in the course of what we're studying is that we prefer to kind of keep all of our energy in one bubble. It makes it easier to handle, but that doesn't always happen. So go ahead, take your hands and rub them together about 15, 16, 17 times. And do you hear the sound? Well, we have mechanical energy in the movement of our hands, but we're losing some of that energy into sound. And now that you've rubbed your hands, place your hands on your cheeks and you'll see that they're warm. And so what we see here is that often our mechanical energy will bleed out, especially if we're talking about friction, into other bubbles. So one of the things we want to say is it's always conserved, always, but not always in the same bubble. So later on, we're going to talk about the fact that friction is a non-conservative force. And that can really throw people, because we're talking about something that's always conserved, but then we say it's a non-conservative force. when we say non-conservative, so if we say non-conservative, we're talking about not always in the same bubble. So there's two different, there were apples and oranges. We're always conserved within this sphere of energy, but we don't always stay in the same bubble. And it's important to know that at the beginning. Now we're going to spend quite a bit of time talking about the mathematics and the formulas of energy. I just want to introduce them here because we're talking about things like the definition. So we have the ability to do work or the act of doing work. And we said that's potential or kinetic energy. So work, which is a capital W, is defined as a force. Whoops, where'd that come from? I got ahead of myself. Force times distance. So if we have a force that is causing something to move over a distance, that's work. And we said that energy is the act of doing work. We also said, or the ability to do work. So we can say that the change in energy, by the way, if you haven't caught on yet, delta always means change. So the change in energy has to do with work. Now, we said that this all ties back to movement. And so here I have force times distance. This is movement. The other way we're going to see when we're talking about mechanical energy is specifically the change in the movement actively. And that's going to be the change in kinetic energy. Now, this one equation sums up pretty much everything that we need to know. Point number 3 and point number 4 are everything that we need to know. But what we're going to have to do before then is we want to work with some of the specifics of this formula. And we want to work with the specifics of each of the types of energy. So before we get to points 3 and 4, we're going to break this out a little bit. And we're going to detail gravitational potential energy, kinetic energy, spring potential energy, and some of these other specific energies. Our takeaways here, energy is the ability to get something done, and it always ties back to movement of some kind, whether we're talking about thermal, electrical, mechanical. It's scalar. How we get from point A to point B is consequential. It's just got a value. It's always conserved, but it doesn't always stay in the same bubble. And we're going to see that this work and change of energy have a direct link together. And so we're going to have a lot of what I call swing equations or layered equations, where it's an equation within an equation. But that gets us started. And in the next video, we're going to talk about what does it mean to define your system, because in order to talk about the energy of a system, you have to know what your system is. So more on that in the next video. Thanks for watching.